So good morning. I'm impressed you folks have come back. And I welcome you back to the third day here of the boot camp. As I am wont, I wanted to begin this third day with a bit of a retrospective of some of the things that we saw yesterday, and then to take that forward with some review of some critical things that got lost in the shuffle, and some new material. So yesterday was a sort of hallmark day in terms of our progression and coverage of material. We used that day to span a bunch of topics which are quite central to agent-based modeling. At this time yesterday, we had created a model which was exhibiting an important feature of agent-based models, namely heterogeneity. But it was heterogeneity in a static sense. So we had agents, and those agents had certain properties which could be drawn from distributions, and that afforded us quite a bit of power, especially given that we could show agents' properties visually in very compelling ways, and we could capture those agents' properties in ways that were conditionally dependent on other properties. So there was a lot there, but we had yet to see many important features as of this time yesterday of agent-based modeling. And these included ability of agents to evolve over time, ability of agents to interact, and ability of agents to be added and eliminated from a population, all of which are very important features related to the practical use of agent-based modeling. So yesterday we hit on all those topics at different points. So we began yesterday's exploration looking at this issue of introducing state charts to agents to capture their evolution over time. And we built up a fairly textured model from the perspective of most agent-based models, which involved interacting state charts. And we had here the evolution of an agent characterized not just for a single condition, but across multiple conditions. In this case, we had one condition, namely weight-related change that contributed risk factors for the development of another condition, namely diabetes. And we saw that we could capture several state charts in a fairly modular way. We could add in description of a new condition without having to worry about dealing with all possible combinations of it in some awkward way with other conditions that we had already represented. And that was fairly empowering in a world where we're often concerned about syndemics of mutually interacting conditions. So that itself was an important insight, and one that distinguishes this sort of modeling from cases of trying to investigate comorbidities in aggregate modeling. We could crisply characterize the progression, not only the division, but the progression of each of these conditions in fairly transparent ways using separate state charts. We then also saw how we could capture the interaction between state charts with a fairly simple mechanism, a mechanism involving a variable that's changed. So depending on where your current weight status, it imposes a different hazard rate, a different chance per year of developing diabetes. And that basic principle could be extended to enable bidirectional interaction. So if someone's diagnosis status with respect to a chronic disease, for example, impacts their physical activity or their motivation for lifestyle change, you might imagine coupling back the other way to the other state chart. And the basic mechanisms we used afford us an easy way of representing that. They're not the only way of representing interacting state charts. And in you can have one state chart send messages to another state chart. You can have one state chart that enables conditions that the other state chart is checking. And you can also have coupling captured in other ways altogether with things like stocks and flows. But state charts are a powerful way of capturing interaction, particularly between discrete categories. So we began the day with that. We then continued on to introduce connections between agents. We placed agents in space, and we could introduce connections that link them, for example, if they lay within a certain distance of one another. And we saw how we could declaratively specify certain built-in networks within AnyLogic. Things like a distance-based network, where their location depends on their connectivity depends on location. Another network exhibiting great locality of connection, a ring lattice network where people are connected with people on either side of themselves and some linearization of the population. We also could capture networks that were not localized, like distance-based and ring lattice, but were global in character. Things like a Poisson random network, where two people are connected, any two people are connected with the same probability P across the entire population. There's no sense of locality. There's no sense of if I have a neighbor, that neighbor and I are likely to have many friends in common. There's no sense of that. We also saw how we could impose small world networks, which are sort of combinations of a local network, ring lattice, with a global network, Poisson random, and we could impose scale-free networks, which are networks that exhibit pronounced heterogeneity in the number of contacts associated with different people within them. Okay, so we can impose these network types, and each of those network types had impact not only on network structure, but in the dynamics of that network, how, say, contagion spread across that network in interesting ways. Leveraging this and leveraging our existing familiarity with state charts, we linked up the state charts to the networks and had people communicate across the networks. And we did that through a mechanism known as messages. So one individual could send another individual messages, and there could be many message types within a given model. We by default used messages encoded as strings, where it would say, I expose you, but we saw how we could actually more robustly do that by using an option list. So then we don't have to worry about misspellings in the strings. We just we say this message type or that message type, and the AnyLogic will double check that what we specified is a known message type. So one agent sends another messages, and that other agent receives them. And where does it receive them? It receives them in their state chart. It's the most common place. So we can have a transition in a state chart that's associated with message receipt. And this is one of a variety of transitions supported in AnyLogic that we had talked about in that first session. Timeout transitions, which are very flexible for imposing arbitrary distributions on residence time. Transitions associated with state or rates, where you have a certain chance per unit time of going from one state to another. Transitions associated with arrival at a destination when you're moving, as we'll see today. And transitions associated with message receipt, as well as a transition that checks a condition. So state charts can handle these messages, allow us to take a message and process it. And we saw how we could introduce these conditional items on state charts with these branches, so that we don't keep them together or powerful. But within that model, we needed an initial message to come from somewhere. And from whence did it come? It came from the environment. So we said at the very beginning of the model that we wanted the main class to send a message to a person inside of it. One of the people maintained by it send a message to a random person. We also noted that we could seed those initial infectives within our model by dividing people up between initial state chart categories. So when they came into the model, some fraction went one way to one category, some fraction went to another, etc. Okay, So that was an interaction of state charts on the one hand and networks in the other, and we went through a variety of different network types to look at their impact on dynamics. In the process, we weaved in some experience with statistics, how we could accumulate statistics at an individual level on their current state or on their state history. For example, how many times they had been in a state where they were overweight, for example, or for how long they had been in an obese state, something along those lines. And then at a global level, we could total up those statistics from individuals in any number of different ways. So we could total them up across the whole population or across population members having certain attributes, et cetera. And that's a very powerful thing. We didn't really reflect on this yesterday, but it's an important difference from aggregate models. Often with aggregate models, in aggregate models, we typically, we will frequently divide a population up into categories. So age groups, for example, 5-year age group, 0 to 4, 5 through 9, 10 to 14, et cetera. And that's very powerful. But when you summarize data, it kind of has to be, it really is awkward to try to summarize it along categories that are finer grained or that are different than those. For example, if you have those 5-year age categories and you want to summarize the characteristics of your population for children 2 years and younger, you would have difficulty because they're all grouped together with those who are older up to 5 years old. And within an agent-based model, we don't really have that same challenge when we have many types of attributes. For example, continuous attributes. We'll see today how you can have continuous age for people. And we can group people in any number of different ways. Just like with empirical data from the world where we have someone's, say, integer age given, we can group them into two-year age categories, 5-year age categories, group people that are 18 years and less, and those that are over 18. We can slice it and dice it in any number of different ways. Such is the flexibility afforded to us by having this fine-grained representation at the individual level. Something I didn't really emphasize yesterday, but a notable feature of having the population individuated into population members. We did further use statistics as computed across the population to enable some graphs. So we saw graphs could be very declaratively created. You drag in a graph, you specify what expression do you want it to show over time, and it would take care of making that happen, which is notable. Speaking from someone who's spent a fair bit of time writing repass code to manually create graphs, it's handy to be able to create them so easily. It's also notable that when we run the models, we can go in there and for many features, we can ask it to dynamically create graphs. Show me this as a graph over time. And it will actually do that interactively, which allows us to explore a model in a fairly flexible fashion, in a way that lends itself to acquiring exploratory insight. The final session of yesterday was I think the weakest of the boot camp thus far, but it did highlight certain features of AnyLogic that are worth noting. Within that final session, we examined the impact of open populations, and specifically we introduced a mechanism in AnyLogic we'll talk a little bit more about this morning, which is an event. We could specify an event which fires off according to a certain schedule, and the event could be set to fire off at a certain time, fire off with a fixed time between events, such as like reporting times. You want to report every year on December 31st, or it could be set to fire off at a certain rate, say a rate of immigration. 10 people per month arrive in our population. And we had a model where we used that event to add people into the population, and we successfully elaborated that model. We saw how we could weave in some UI elements, some user interface elements. We could add a button to add people. We saw how that could be done. We saw how we could click on people and make them disappear. And then we added, using a state chart, a representation of natality, so births, and mortality, deaths of individuals, in a way that would remove them from the population. But there were a few things that came up in that were rather different than what I was expecting based on a previous exercise we had done like that in AnyLogic 6. And I felt that sort of compounded itself and led to some confusing features of the situation. I felt the clarity was a lot lower than it could have been, and it raised some artificial barriers. So we're going to be sort of recouping some basic aspects of that situation this morning to lend better clarity to those concepts, because they were marred by distractions having to do with where functions lived and what arguments they took and what order they were in. And it got in the way of some of the understanding. So I apologize for that, but we're going to revisit that this morning. It shouldn't take that long, but we'll hit on those basic points with greater clarity. Okay? So any questions that came out of yesterday before we dive into some sit-ups? Questions? Yes? Yeah, we're going to be talking about replications. It will occur quite possibly by the end of the afternoon today. But for didactic reasons, I'm going to be introducing them at a time where we have mechanisms to summarize over these many replications, and I'm gonna do that in a later lecture, because it's very convenient right now to deal with particular runs of the model with standard graphs. But we'll be coming to that, and likely it will be today. Okay? So good. And I did note in my introductory remarks on ABM that typically we want to run the model many times using what are commonly known as realizations, what AnyLogic calls replications, so that we can gain confidence that what we see is not merely a fluke of a particular run, but is a structural feature of the behavior of the model. So thanks. We'll be coming to that. Any other questions? Okay. So we're ready to go. Okay. So I'm going to